In this video, I'm going to perform a virtual experiment to measure the specific latent heat of fusion of ice. We are going to be using this equation for specific latent heat, where E is the heat or the energy that is transferred, M is the mass of the substance, and L is the specific latent heat. We are going to melt ice at 0 degrees Celsius, so the more energy we put into our ice, the more mass of ice will melt. By measuring the energy we put into the ice and the mass of ice that melts, we can then determine the specific latent heat of fusion of the ice. We are going to use an electrical heater to heat up the ice, so power is going to equal the potential difference across the electric heater multiplied by the current through the electric heater, and both of these quantities can be measured. Remember that power is defined as energy transferred divided by time. So the amount of electrical energy transferred is going to be equal to the potential difference across the heater multiplied by the current through the heater and multiplied by the time that the heater is turned on for. Now, with our heater in our simulation, the potential difference across it and the current through it are going to remain constant throughout the experiment. This means that the change in energy that we put into our heater is going to depend on how long the heater is turned on for only. We can substitute this into our equation for specific latent heat, and we find that the specific latent heat will be the voltage across the heater multiplied by the current through the heater and multiplied by this ratio, the amount of time the heater is on for divided by the mass of the ice that melts. So we're going to perform an experiment where every 10 seconds, maybe every 30 seconds, we record the mass of ice that is melted. We will then plot a graph of time versus mass, which seems like an odd way around. But we do that because we're going to be interested in the gradient of this line, which is delta T over delta M. Once we've determined the gradient of this line, we can then multiply that by the potential difference across the heater and the current through the heater to determine the specific latent heat of fusion of ice. So to perform the experiment, we're going to use this simulation that was produced by Dr. John Nunn of the National Physical Laboratory. This is part of the Virtual Physics Lab suite, and Dr. John Nunn has given me permission to use this in my videos and tutorials. You can see that the ice is at 0 degrees Celsius, and so we don't have to worry about heating the ice up to 0 degrees Celsius before we start. People who know me will know that I'm a big fan of spreadsheets, so I'm going to record the data from my experiment below in this little spreadsheet window. So let's switch the heater on and let's start recording our data. Collect and time. And so in 10 seconds we will have collected. Let's just keep watching. I made that 10 grams. In 20 seconds we will have collected. Let's keep watching. 21 grams I made that. In 30 seconds I made that 31 grams. In 40 seconds 42 grams. In 50 seconds 52 grams. In 60 seconds 62 grams perhaps, and in 70 seconds that was 73 grams. Okay, so we can now continue this if we wanted to get as large a range as possible. But I'm going to stop here. You want as large a range of results as possible because the larger your range of results, the more accurate your final answer will be. Now at this stage, I'm going to convert my masses into kilograms. I don't need to. I could work in grams and then do the conversion at the end, but I find students find it easier if the conversion is done at this stage. So now I can plot my graph of time on the y-axis and mass on the x-axis, which I've done here. Reassuringly, you can see that the line is straight, and that's what we would hope would happen. Now the gradient of this line is delta t divided by delta m. And there's an Excel formula I can use to compute that, which is slope. So we type equals slope, our known y's are the times, and our known x's are the masses, close bracket, enter, and that gives us the gradient. The units of this gradient are seconds per kilogram. And you can see from the equation above, we also need the potential difference across the heater, which is a whopping 80.7 volts in this case, and we need the current through the heater, which is 3.67 amperes in this case. So we're going to include those in the spreadsheet as well. And according to the equation that we wrote above, if I multiply these three numbers together, that will give me my specific latent heat of fusion of the ice. Now when you look at this number, 284,000 roughly, to three significant figures, 284,000 joules per kilogram, it sounds like a big number, but it's not actually high enough. And so the question would be, why is this number too low? And it's because of how we performed our experiment. We did not take into account the fact that the ice is melting due to absorbing heat from the surroundings. There's other heat gains, not just the power from that is provided from the heater. And so we have to determine what they are ourselves before we can do our final calculation. And the way I'll do that is I will turn our apparatus on for 70 seconds and see how much mass we have melted, how much ice mass we have melted without the heaters turned on. And so I've turned the heater off, and I'm going to collect and time the water that melts in 70 seconds. And I'm going to use that to improve my answer. Of course, I'm not just going to leave the video playing for 70 seconds while I watch ice melt. I will pause the recording. And there, in the 70 seconds, we've melted 10 grams of ice without the heater even turned on. So what I've done is I've used the fact that 10 grams was melted in 70 seconds, scaled it for all these other times, and subtracted that mass that was melted due to the ambient heating of the ice. I've subtracted that mass from all of these values. And so these are my new values. This is the amount that was melted because of the heater only. And because I've used a spreadsheet, it will do the calculation again for me automatically and give me about 332,000 joules per kilogram. So if I type in 332,000 joules per kilogram, the unit in this simulation is in fact wrong, and press check, it will tell me well done. And that's it. So if you found this video useful, please like and subscribe to help me promote these videos further, and don't forget that there's a live tutorial every Saturday morning at 10 o'clock in the morning UK time, where you can get live interactive help via YouTube.